How do you turn a sample return tragedy into a triumph? We reflect on NASA's Genesis mission, this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. The Genesis mission was NASA's first dedicated mission to capture and return samples of the solar wind. But instead of a smooth landing, its capsule crashed in the Utah desert at over 300 kilometers per hour. Against the odds, scientists managed to salvage the mission, unlocking insights into the formation of our solar system that we're still piecing together 20 years later. This week, we're joined by Amy Jurewicz, Assistant Research Professor Emeritus at Arizona State University and JPL Project Scientist for Genesis. She shares the challenges and triumphs of space sample returns and what Genesis taught us about the sun. And of course, we'll check in with Planetary Society Chief Scientist Bruce Betts as we look back at solar science during the Apollo program. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. For centuries, scientists have sought to unravel the mysteries of our sun, how it formed, how it impacts our solar system, and what secrets its chemistry might hold for the origins of our planets. In 2001, NASA launched Genesis, a mission designed to capture pristine particles of the solar wind and return them to Earth for the first time since the Apollo program. Genesis floated at the Earth-Sun L1 Lagrange point for 2 years, spreading delicate collectors into the solar wind and gathering the material that was streaming from our star. But as Genesis made its return to Earth in 2004, 20 years ago, disaster struck. A design flaw prevented the deployment of its parachute, sending the sample return capsule hurtling into the Utah desert at over 300 kilometers per hour. That's about 200 miles per hour. The impact shattered many of the sample collectors and contaminated some of the long-awaited solar material. But like so many great space missions before, the Genesis team refused to fail. Scientists, including our guest, Dr. Amy Jurewicz, painstakingly recovered and decontaminated the samples, developing new techniques to study the solar particles from the damaged wafers. Despite the crash, Genesis achieved its primary science objectives, providing groundbreaking insights into our sun's composition, data that continues to refine our understanding of planetary formation and space weather to this day. Dr. Amy Jurewicz is an Assistant Research Professor Emeritus in the School of Earth and Space Exploration at Arizona State University's Busek Center for Meteorite Studies. As a materials scientist and planetary researcher, she's worked on NASA's Genesis since 1998 and served as JPL's project scientist for the mission. She was key in archiving Genesis materials and preparing for their return. And bonus fact, Amy also contributed to the Stardust mission, another groundbreaking NASA sample return mission that returned particles from a comet's coma. The lessons from Genesis paved the way for future sample return missions, proving that science can triumph even when things get really complicated. Hi, Amy.
Hi, it's good to meet you.
Oh, good to meet you too. And congratulations on passing this 20-year anniversary since the landing of Genesis. It's been quite a while, but I'm really grateful to be able to share this story at this moment in time because it's relevant to so much of what's going on in our lives in space, both the sun at solar maximum and what's going on with all of the solar weather. But also, we just got the results back from the OSIRIS-REx samples. So it's a pertinent time to talk about the history of sample collection.
It is, and I will talk to you about it later, but we actually have some Genesis information that's been applied to some of those asteroid return samples.
Oh, that's fantastic. And makes a lot of sense after diving into the history of this mission. I think when a lot of people think about the Genesis mission, and myself included for quite a while, the thing that people focus on was that horrible day 20 years ago when it came in from outer space and absolutely crashed into the desert. But what I think people don't realize is that wasn't the end for this mission. And in fact, you guys ended up being able to recover these samples and actually accomplish the entire purpose of this mission despite all of that tragedy. And it's really important to understand that sometimes things go wrong in space, but through that perseverance, you can actually still accomplish your mission anyway. So it's been really beautiful going on the journey of learning more about this mission. And now I have a whole new appreciation for what your team accomplished.
Well, it's been hard over the past 20 years, but whenever you get a sample back from space, you can always work with it. And that's what the people who were covering the disaster didn't understand, is that as long as at least some of the sample had survived, we could work with it, and we would eventually learn how to analyze it and get data. We were also a bit lucky in that the Genesis concentrator, which was one of the major parts of the mission, that these solar wind collectors came out almost untouched. One of them was broken. So we actually got some of the most important science early on because we had to learn how to work with those targets, which did have some radiation damage and had brine from the desert rains the day before the crash, but it went almost as planned. So by 2012, we actually had that part of our mission accomplished.
Of course, this sample collection was made far more complicated by the fact that when the spacecraft came down, it didn't actually land in the way that we anticipated. I believe that the initial plan was that as it came in and the parachutes deployed, there was a helicopter that was supposed to intercept the samples on the way down. Is that right?
Oh, yes. Those poor guys had been practicing catching the, simulated return capsule, and they were so good at it. And it would have been wonderful if they caught it. It was all set to go. They're out there circling, but the drogue chute never opened, which meant that the actual parachute didn't open. And it came in at terminal velocity. And it was literally modeled as a meteor by some of the researchers at the time, because they could see it come in and they could see how it was ablating. And it was terribly upsetting. I was in front of about 500 people with somebody who was the project manager who'd left the mission a little bit early to go to other things. And I had just finished telling everybody how much work we'd put into a experiment out of Berkeley, which collected radioactive isotopes from the sun. And if we'd done it wrong, the drogue chute wouldn't open.
Oh, no.
I felt, oh my God, I know it wasn't us, but they don't know that.
What actually did cause the drogue chute to not deploy?
When Lockheed Martin redesigned the spacecraft, or the sample return capsule from Stardust's sample return capsule, the engineer drew an arrow backwards. And that backwards arrow put the pressure sensor in backwards. So the pressure sensor never saw the atmosphere. So the parachute didn't open because it didn't know it was in the atmosphere. It was just somebody put that arrow in backwards and nobody caught it.
A few months ago, I was speaking with Dante Loretta about the OSIRIS-REx mission, and there was a moment for him and the team where the communications on the sample return as it came in were a little slow, and they hadn't heard that the drogue chute had deployed. And he said that in that moment, he specifically thought about your team and about what you must have gone through during that moment and how it was all alleviated for him in a few moments, but you had to live it.
Yeah, it was amazing for all of us. I think while it was coming in, we could see that there was something wrong. It was spinning, which it shouldn't have been spinning. And it was clear that the drogue chute hadn't opened when it should have, or it wouldn't have been spinning like that. There was always that, well, maybe it's just delayed for some reason, maybe. But then when it finally hit, we just had to face reality. And of course, everybody in the place was horrified, and we're supposed to say something smart. And I heard somebody ask the person who had previously been the project manager, what the red stuff was around the capsule, and I thought, oh, it's the blood of the science team.
Oh.
And then I had to think, did I say that out loud?
Well, in moments of great stress, you never know what's about to come out of your mouth. But even in the aftermath of that, you kind of had to get it together and then implement this contingency plan that you hoped you were never going to have to implement. What did you actually have to do in order to get all these samples together and hope that you could actually scrape something out of this?
Well, I personally, with the person I was with, raced out to UTTR, where we admitted we had reason to be there. And we waited just outside the clean room while they inspected the sample return capsule, which took a very long time because, for one thing, the parachute had not deployed, which meant it had live ammunition in it, ready to deploy. It also had a battery in it, which was likely emitting sulfur fumes, so that was dangerous. It took quite a while of us sitting there, rubbing our hands together, waiting for them to be able to put together the pieces of this spacecraft and bring it in. But when it finally showed up, it looked absolutely horrible, but we inspected it. We realized that there were still some samples there that were attached to the collection system. They could see that the concentrator targets looked at least mostly intact, and the few pieces there were inside a screen that was meant to deflect hydrogen because you didn't want to concentrate the hydrogen. You would destroy all your sample. So they had all the pieces. The poor person at Berkeley who put out the oils that were to collect the radioactive isotopes had a total mess to work with. He is still trying to get data from that. It's been working for 20 years, and he hopes that next year he will be able to do an analysis. He lost probably 2/3 of his sample, but luckily progress and instrumentation may allow him to actually do a run. What else did we do? We tried to figure out what we could do to sort the different sample types, is what I did, because I was one of the people who could recognize the difference between samples that were almost the same color. Then the people from NASA JSC were in the clean room, or seeing what they could bring into the clean room and trying to inspect different parts of the spacecraft to see what was there. We went around, got things that would help us do sorting. I went out and I got Post-it notes. We were sticking these ultra clean samples to the back of Post-it notes because instead of being 4 inches, they were millimeter size, and we knew we might be able to use them. And cataloging them and photographing them and sorting them and all those things. It took, I don't know how long at the Cape. I had to leave early, but I remember it going on for several weeks. I sent them some vials and different things they could try to sort these samples. And then eventually they got it all packed up and secured, and they moved it off to the Johnson Space Center, where it's still being sorted today. They still have these jars that they call picking pots. If somebody needs a sample a few millimeters in size, you can go to the Johnson Space Center Genesis Curation, and if they let you, you can go in with a pair of tweezers and pick out picking pot samples.
Oh, I just imagine all of you in the desert with tweezers just trying to pick little pieces out, and all of the complexity of trying to figure out which part goes with which is the biggest puzzle ever. But then you have to figure out how to decontaminate all of this and actually figure out how to get science out of it. Was there some special way that you had to remove contamination from these things, or did you just go for it?
Well, that's another story. I should say that somebody brilliant at the beginning of the Genesis mission, when they were designing it, realized that there was a small chance that some of the collectors might break on the return. And so they made the collectors for the different solar wind regimes different thicknesses. So after the crash, Johnson Space Center could go through and measure the thicknesses of each of these little fragments of sample and tell you what solar wind they collected. So that was part of the science. The dirt, some of it we were able to take off. They take off routinely with ultrasonic cleaning, but that was a long road before they actually started doing that because they weren't sure whether the water would affect the solar wind. They had to prove that it wouldn't on at least the samples they were doing the ultrasonic or megasonic cleaning. Actually, we did that with almost all the samples. We would radiation damage flight spare materials and then try cleaning processes to make sure that the cleaning didn't ruin the solar wind sample. Many of the current analyses are being done with these small samples from the back side. We turn them over. They're glued to a substrate and then thinned from the back side so they can do depth profiling using either laser ablation or more likely secondary ion mass spectroscopy, where they just ablate an area with an ion beam and then they look at the secondary ions that come off and avoid the contamination completely. That's something that is occasionally done in the semiconductor industry, and it proved very useful to us. I can't tell you how many things we looked at. We have an entire team for years who, although we did other things as well, when somebody wanted a sample but they couldn't figure out how to get rid of the contamination, we would work on it and we'd try different things and do our best to ensure that when the sample was finally cleaned, it didn't ruin the solar wind sample, because the solar wind is closer to the surface than the human hair is thick. So it didn't take much to actually ruin or eliminate the entire solar wind sample. And how we cleaned it depended on what material we were cleaning, which is one of the reasons I stayed with the mission. I'm not a cosmochemist, but I am a materials engineer to at least some people. A ceramic engineer by some training. So I figured I was the one who was needed to help with some of this material science, and I stayed with the mission. I was planning to leave the mission after the sample came back and just hand it over to the cosmic chemists. I figured I'd be there to answer a few questions, but I never thought I'd be spending the rest of my life working on it.
Honestly, the amount of effort that had to go into making sure that you could actually use all these samples after all of this has just been absolutely prodigious. And I'm sure that your team has learned so much about sample recovery, but also about how to prevent issues like this from happening with other sample return missions. And you mentioned this a little bit earlier, that you'd actually worked with the team from JAXA that was trying to retrieve samples from Itokawa. Have there been other sample retrievals that you've worked with as well?
Well, I didn't work with them. I just know people who have, but they've worked with Genesis. And I think people more and more are learning that Genesis has a lot to offer. I actually heard a space weathering person talk about what they learned from Genesis. And we know that the solar physicists are modeling solar wind fractionation, or lack of, depending on the element, inspired what we're learning from Genesis. I mean, there's just so many implications. I'm hoping that materials engineers will eventually take a look at some of our work, but engineers don't usually look at the meteoritics literature. Who knows? Maybe if some of them are interested, they'll to your podcast, they'll go take a look.
Let's get into some of the science results. Genesis wasn't just a standalone solar mission. I think what I really learned as I was researching this is that it was built on the foundation from earlier research, like the Apollo solar wind experiments. How did Genesis expand on that work, and what kind of new capabilities did it bring that Apollo couldn't?
The original Apollo, foil collection was only at most for a few days. I mean, the astronauts weren't on the surface of the moon very long, and they didn't leave the samples there. But then again, they had great big sheets of aluminum or platinum, which they just dissolved the whole surface of the sheet and they got a measurement. Whereas in Genesis, we had our samples out there for 2 years. And they were smaller samples, but technology has improved since the Apollo days, so they didn't need larger samples. The other thing that Genesis did was that they collected different portions of the solar wind while they were out there. So they collected the bulk solar wind like they did in Apollo, and that was, I think, for 832 days as opposed to maybe 3. But they also deployed, they had a stack of arrays. The top one measured bulk. The ones underneath were stuck out like big tennis rackets when the sun did things that they calculated would give them a different solar wind regime. So they collected slow solar wind, fast solar wind, and coronal mass ejections. And we have gotten information from those that not only help correct for any fractionation in the Genesis sample from making the solar wind. Solar wind is processed material, and they wanted to be able to check how that material was processed and whether it affected the data. But and it turns out, at least for some of the elements, not all that much. For some of the elements, it can be a factor of 2, but now they've got information to go back and fix that. But they also have been discovering things about solar physics of great interest to solar physicists. And in fact, since the return, and since we've started getting data from the return, it's been hand in hand with solar physicists. There was another collector that was called, it was called the ADM collector, but it was a bulk metallic glass, which is a weird thing that they use on golf clubs, but we used it as a solar wind collector. And the young postdoc who analyzed it was able to show that, he not only measured the solar wind, but he was able to show that the profile of the solar wind could be mirrored in the lunar regolith as long as you accounted for sputtering over the millions and millions of years that the regolith was exposed to solar wind. And that actually changed the cosmic chemical interpretation of the lunar regolith. And that was done in 2007, which wasn't that long after the crash.
But this mission didn't just improve on what Apollo did. It was inspired by someone who had firsthand experience with those early experiments. And I know you were very close with him because he was the PI for Genesis. Can you talk a bit about Don Burnett and how his work with Apollo helped shape the vision for the Genesis mission?
Most people wouldn't connect the Apollo foil experiments to Genesis just by looking at it. And they can look at it. They can go back to Apollo 11, and there's a photo that Neil Armstrong took of Buzz Aldrin standing next to this huge, totally blank flag. And that flag is actually the first of the Apollo foil experiments. But one of the people who trained astronauts during Apollo was Don Burnett, who was the PI of Genesis. He knew about the Apollo foil experiments. He knew what the astronauts had to do. He knew the amazing results they got from just planting those flags on the moon for a few hours to a few days. And he was determined that he was going to have a mission of his own at some point where you could go out and collect solar wind for a longer duration. And his goal was for cosmochemistry to get both isotopes so they could learn more about the processes which form the solar system from the protoplanetary disk and the protoplanetary disk from the solar nebula, because every process changes the isotopes of the elements. But the other thing he wanted to do was to be able to model the formation of the solar system using a baseline of solar composition measured from solar matter. And most people out there are going to say, well, don't they already have that? And the answer is no. We have some spectroscopic data of the sun, but it's not good enough for precise modeling of processes. So what everybody has been using for about the past 75 to 100 years is the composition of a rock that fell in France called a CI chondrite. The one that fell in France is Orgay. There are a few others. And that rock has a composition which fits into the error bars of the solar spectroscopic work. Don Burnett has been trying since, well, at least 1989 when I read one of his papers. Well, I didn't read it in 89. He wrote it in 89. But he's been trying ever since to get people to use solar matter for all this modeling. And of course, there's been no source of solar matter except the solar wind. Now, he's been working on it for so long that we just got a paper out last year working with two amazing solar spectroscopists. Don and I were able to show that, yes, indeed, the CI chondrites are not exactly solar. And it just so happens that what we found is also consistent, although I think maybe a little bit broader scope, than an astrophysics model that says exactly the same thing. That one of the reasons that it is so, CI chondrites are so close to the original protoplanetary disk is simply because Jupiter got in the way and they couldn't fractionate all the way out to where the CI chondrites were formed. But on the other hand, that didn't mean that there was no fractionation. It just didn't fractionate more than 10 to 15%.
And we've been learning so much over the years between Genesis and now we're all the way at Parker Solar Probe, literally flying through the corona of the sun. So being able to compare the data across these multiple solar cycles, and now we can get close enough to really kind of pinpoint those origins of the solar wind. But at the time, there was a lot that we didn't know. This spacecraft was positioned much further away from the sun than a lot of other missions have been more recently. It was at that L1, the Earth Sun Lagrange point 1. Were there any specific types of solar wind or measurements that you wish you could have taken closer to the sun, or did that meet all of the constraints that you were trying to look at?
We were fine for what we were doing. I don't think we would want to be closer. There'd be way too much damage. We might someday want to put something out closer to the asteroid belt, but it would have to be there forever. Because it goes away as a square of the distance from the sun, and actually it's less than that because it goes out at the surface of a sphere as it goes away from the sun. So it would have to be out there for more than 2 years. But the interesting thing is that we were there at the L1 point with the ACE spacecraft, and they had a solar wind monitor. So we have been working in great detail with them. It was from their data that we were able to determine what the energies of the solar wind that we were collecting were before they hit our collector, and we could use that for our modeling. And there have been some really interesting things that we have done for them. I mean, they've reworked their data twice based on information from Genesis. They've changed their algorithms. And there is one paper that is in preparation that I would have liked to seen come out 5 years ago, but amazing things require extraordinary proofs. So over the past 5 years, the group in Japan that did this have been working with the ACE people and other solar physicists to get together a paper. But the people in Japan were actually able to measure a coronal mass ejection that happened in 2003. It saved all the spacecraft. The ASWICS tried to measure it, but its electronics were saturated at the peak. Like, they're lucky it didn't burn anything out. But Genesis only had to hold this paddle out there and collect the solar wind. It didn't have any electronics. So when we brought it back to Earth, they were able to actually isolate the signal from this coronal mass ejection. And I think that's wonderful. It turned out it was much larger than any of the solar physicists or space weather people realized. That really doesn't make any difference because they know what the effects were. On the other hand, if they're going to go out in space with people there, they should know what's hitting the spacecraft.
We'll be right back with the rest of my interview with Amy Jurewicz after the short break.
I'm Jack Corelli, Director of Government Relations for the Planetary Society. I'm thrilled to announce that registration is now open for the Planetary Society's flagship advocacy event, the Day of Action. Each year, we empower Planetary Society members from across the United States to directly champion planetary exploration, planetary defense, and the search for life beyond Earth. Attendees meet face-to-face with legislators and their staff in Washington, D.C. to make the case for space exploration and show them why it matters. Research shows that in-person constituent meetings are the most effective way to influence our elected officials, and we need your voice. If you believe in our mission to explore the cosmos, this is your chance to take action. You'll receive comprehensive advocacy training from our expert space policy team, both online and in person. We'll handle the logistics of scheduling your meetings with your representatives, and you'll also gain access to exclusive events and social gatherings with fellow space advocates. This year's Day of Action takes place on Monday, March 24th, 2025. Don't miss your opportunity to help shape the future of space exploration. Register now at planetary.org/Day of Action.
Especially now that we're entering into this new Artemis age and thinking about sending people outside of the protection of our Earth's magnetosphere for extended periods of time. Was that coronal mass ejection in 2003 the same one that caused the Halloween aurorae, as some people call them?
Yes, that was exactly the storm that they isolated.
That's really cool because in recent months, I was speaking with Vincent Ledvina, who's also known as the Aurora guy. That was the inciting incident that got him into aurora photography and led him on that whole scientific journey. So it's cool to learn more about that.
Well, they have, I should show you at some point, they have the amount of hydrogen and helium and the velocities that came out of that storm. And it is a lot more than they were able to measure with spacecraft simply because those heavy storms saturated all the electronic equipment.
And a good opportunity, too, to teach us more about space weathering and really lucky to get that coronal mass ejection at that specific moment in time, because that created aurorae so vividly, into latitudes that don't usually experience that kind of thing, that I think that was like a real moment for people to begin to actually worry about space weather, at least in our more modern world.
Yeah, and it, it was a big storm, but it wasn't as big as some. And in fact, there is a new abstract, it hasn't been reviewed yet, from the same group that looked at some of the Itokawa samples and found the fingerprint of another storm that was 240 times as large as the Halloween storm that hit the regolith of the asteroid.
Oh my gosh. I know this isn't the subject of the interview, but do they know how long ago that happened? That's amazing.
I would have to look at the abstract, but it's going to be presented at the Lunar and Planetary Science Conference, so you may be able to talk with the person who did the work.
One of the major goals of Genesis was measuring isotopic ratios in the solar wind. Why were these isotopic measurements, and especially for oxygen and nitrogen, so scientifically important?
The isotopes are important because the different processes that happen or could have happened in the solar nebula and protoplanetary disk will affect the isotopic ratios. So if you know the isotopic ratios, you can compare those with models of the formation of the solar system from the protoplanetary disk. And you can also look for inhomogeneity in oxygen and nitrogen in the protoplanetary disk and solar nebula. So this is the stuff of cosmic chemistry. Most of the team were cosmic chemists, and Genesis was a cosmic chemistry mission. But I usually leave that to the experts, and I go to the things that they're not as interested in, like space weathering and coronal mass ejections. Basically, the sun changed the composition of the solar nebula because of its light, and it reacted with the particles and things like CO and changed the isotopic composition locally. And with the nitrogen, the weird thing about the nitrogen is the solar nitrogen is nothing like that of the terrestrial planets. It actually looks like Jupiter. And that means that the terrestrial planets evolved in a way that gave them a different nitrogen isotopic ratio. One of the people from WashU early on wrote a paper on his noble gas isotopes that gave a heads up on some of the ways it might have changed in Earth's atmosphere by losing the early atmosphere to space. And I know that our colleague in Nancy has several papers on how using these nitrogen isotopes, you can look at inhomogeneity throughout the original solar nebula. I mean, it's fascinating.
That's something so beautiful about this kind of sample collection, because it gives you the opportunity to study so much, not just the history of our solar system and its formation, but things that impact us more regularly. Like, we're going to need to understand more about space weathering as we process these samples, but also because of the longevity of the time that we're going to be in space. There are a lot of things we need to consider about the degradation of our spacecraft, or, putting things on the surface of the moon. So there are so many applications for this kind of sample return.
There are, especially because people have been ignoring the slow speed solar wind to some extent because, it's slow, it's not high energy. They figure they can, especially cosmic chemists and people who do space weathering research on planetary materials, have kind of ignored it. It's just not have been of interest. But it turns out that a lot of what we see in telescopes in terms of changing color can also come from that slow, steady, low energy solar wind. Whenever you bring back a sample, you have a goal for that sample. And Genesis has been conscientiously working towards that goal, and we've met most of them. But whenever you bring back a sample, it's a surprise package, and you find many, many, many things that you never expected. And some of those things are of interest to a wide variety of people.
How does all this information teach us more about the origins of the different types of solar wind?
We have people that we've worked with who actually model the amount of these different trace elements. I mean, most people model the amount of solar wind. When you put a spacecraft into space, they almost all measure hydrogen or helium. But things like oxygen, nitrogen, silicon, carbon, they're all there, but they make a trivial percentage. I think it's like 1% of the solar wind, and it's the entire spectrum of the periodic table. So very few spacecraft measure all that. And those that do, I've seen some of the plots. I think they're scary. They look like somebody took several pots of paint and dropped them on a grid, and then they have to go through and determine which ions they're measuring. And the ions coming out of the sun are like nothing you've ever seen. I mean, we've got we don't have oxygen +2, we have oxygen +7, we have oxygen +8. This is the sun. Everything is a plasma. It's not like anything you've learned in freshman chemistry. So it's very complicated. So I think that a lot of people are very happy to see the clean measurements of different types of solar wind that we know are good to, even the bad measurements are probably good to 10% when they're published. And they can put these in their models of how the solar wind is formed. I work with somebody at NRL who has been mentoring me. He's going to have a talk at the Lunar and Planetary Science Conference, if anybody's interested. He is working with the rest of the solar physics community, of course, but he also models solar wind formation based on forces in the corona of the sun that create waves. And those waves, basically, they're like waves in the ocean. They slosh back and forth and back and forth. That he uses. And then when that creates this wave, it will eventually create a loop that breaks, and those ions will go streaming away from the sun. But while it's sloshing back and forth, the heavier things get left behind and they start to separate. And you can look at the ions, what they are versus what you think they should be based on Earth, and look at the differences. And that's what he's modeling. He's modeling those differences in ions and seeing what models of the solar corona fit the Genesis data. And of course, he's doing it without Genesis too, but that's one of the uses of the Genesis data, is to help constrain some of those models. And when he looks at the fractionation, he helps us because we need to know whether the Genesis ions are fractionated as well when it's applied to cosmochemistry.
Thankfully, this data is available to scientists of all walks of life. So if there's something one person misses, someone else will figure it out, or even decades later, come back around to it to help suss out some data from a different spacecraft. And it's beautiful watching these results roll in decades after the missions that accomplish them, and really speaks to the power of each and every one of these spacecraft. It's not just about what we gather in the moment. It's about the entire history of grad students and technologies and whole realms of science we might not even have thought to explore without the missions that came before.
Well, it wasn't until 2015 where some people reviewed the ACE data for a second time and realized that they could see small amounts of fractionation in some of the lithophile elements like silicon and magnesium. They never even thought to look for it because they plotted everything against oxygen. If you plot it against oxygen, you can't see anything. If you do what Genesis does and plot things against magnesium, you can see small variations with solar wind speed and whatever it is they decide to plot against based on where that particular quanta of solar wind has come from. And it's amazing what we've inspired. And I'm thrilled that they got so much cosmochemical information out of it, but I am just as thrilled that they were able to get so much solar physics and space weathering and just space weather and just other information. And I hope they will continue to do that. Not to mention that they're working on developing newer, better instruments, which I hope is in part inspired by Genesis. It's inspired by a lot of other things as well, but at least in part inspired by being able to measure these samples.
Do you think that there are any major lessons from particularly the space weathering that was caused to all of the collectors and instruments on board that are going to help us in the future as we're making these instruments?
Well, I think that the very fact that they know that some of these CMEs have a lot more hydrogen and helium come out at higher speeds than anybody knew will help them in their testing, because they have specific vacuum chambers with, ion beams to test their spacecraft and instrument components. And now they know they're going to have to do it for longer times and maybe at higher energies. but not really high energies. Everybody tests at the really high energies, but we found that these low energy solar wind impacts can do a lot of damage.
Which is both frightening and good to know.
Well, it doesn't do a lot of damage here on Earth because we've got the atmosphere. They're not going to make it through. Some of the higher energy things will make it through, but we've already seen what that does. But we have to worry about is the thing sitting out in space.
Yeah. And we don't have any good, solid solutions yet to how to protect our long-term space travelers. And this is the kind of data that could potentially save people's lives in the long run. If we know that we have to worry about not just the fast solar wind, but the slow solar wind and this persistent kind of weathering that can happen to both spacecraft and unfortunately to our bodies, that's a whole context that could make a big difference in the future.
Well, especially if you're going someplace like Mars and you're going to be in space for 2 years minimum, and then you're going to be at a place with less atmosphere to protect you, you have to really have a good feeling for what's going to come at you and what happens when you want to come home. You're going to be out in space a really long time, and you need to know exactly what those energies that might hit you are going to be while you're sitting there in a spacecraft and can't get out of the way.
And they're going to depend on all of the satellites and instruments that we send along with them to make sure they can communicate, but also monitor what's happening on the ground. We need to make sure that all those instruments aren't affected by this as well. And if we're going to be trying to build long-term space stations like Lunar Gateway around the moon, we need to make sure that doesn't fall apart as well. There are a lot of consequences to this.
Yeah, I mean, everything gets weathered. There's no way to avoid that. But if you think you're going to need help during a solar storm, you're going to need to have specific types of protection. I mean, obviously they can do it because they've got the solar probe going right next to the sun.
Right? Oh man, Parker Solar Probe is such a wacky technology.
But you don't want to carry all that stuff with you if you're going to Mars. It's heavy.
Right. Just going around Mars with a giant suit made out of huge, carbon shields. Well, they're not huge. They're pretty thin, honestly. I'm surprised. But our ability to study the sun has advanced so much in this time, and we've learned so much, and we're still able to compare all these generations of data. It is a beautiful thing to see, and I cannot wait to see what happens in 100 years when we have this long-term look at the solar cycle and the solar wind and all of its impacts, and learn more about the origins of our sun and our solar system and how all that differentiated out. There's so much left for us to discover.
The interesting thing that, at least I think is interesting, that our colleague at NRL is going to talk about at the Lunar and Planetary Science Conference is that information from, I believe it's a Parker Solar Probe, but all the information from the recent solar physics satellites have determined that there is a different way to look at fractionation and how the solar wind is moved out of the sun, which is actually confirmed in good part by Genesis, because we haven't seen large amounts of fractionation even in places where as much as 10 years ago we were expecting to see it.
Yeah, that's quite surprising. I wonder what causes that.
Well, it depends on the mixing inside the atmosphere of the sun, how well it mixes or doesn't. When you've got the waves going back and forth, I think I mentioned that you do get some separation between, the heavier and lighter elements in the plasma. But the other factor that wasn't included was how fast you can diffuse fresh solar material into that. If you can diffuse that fresh solar material into that wave quickly, then you really don't see much of the fractionation. If it takes an awful long time to get there, then you get a lot of fractionation. And I think what they're doing is they're finding out that there's more mixing in the sun than they previously understood.
Well, thank you. It is such a long saga, a tale of triumph through this tragedy of your spacecraft crashing. And yet, despite that, you not only accomplished the main goals of this mission, but found surprising science far beyond that, and have shared it with so many other missions that have now succeeded in their sample returns and in their solar science. This mission, even though it's been 20 years, is still making such a big impact on what we know about the sun. And I really appreciate you coming to share just a small part of this story and everything that you've learned from it.
Well, it's my pleasure. And I would like to leave your listeners to understand that we're not done. There is a lot more that can be done. I'm not sure after 25 years on Genesis that I have the energy to do a whole lot more, but if anybody out there wants to do it, I'm willing to help get them started.
Beautiful. Well, thank you so much for joining us, Amy, and good luck on all this. And I'm hoping you're about to get a bunch of emails from potential students who want to help out with this, because there's so much left to learn, and we're going to need everyone's help to figure out this mysterious universe together.
The pleasure is mine. Thank you so much for having me.
The story of the Genesis mission is a testament to the power of perseverance and the ingenuity of space mission teams. And yes, I know that's a joke about Mars spacecraft. I couldn't stop myself. Even when things don't go as planned, scientists find a way to salvage, adapt, and push forward, ensuring that every mission builds on the lessons of the past. And just as we learned from the Genesis mission as we're creating future sample returns and solar missions, Genesis learned from the Apollo program. We'll explore some of that history next in What's Up with our chief scientist, Bruce Betts. Hey, Bruce.
Hi, Sarah.
Man, I did not know enough about the Genesis mission before I went into this conversation. And I know it's been 20 years since it crash landed in Utah, but what a fascinating mission. Do you remember when that happened, when it actually crashed?
Oh, yeah. That was an oops. Yeah, and then it's been amazing, and I look forward to listening to this interview because I know they've recovered a lot of the science and a lot of work to do it. But it was like, wow, that's smart people like me looked at the pictures and said, that's not good.
No, but the story is just so intense. Them literally combing through the desert with little tweezers, trying to figure out how to put everything together after the fact. But the unique situation about how they gathered these solar samples is very different from something like, say, OSIRIS-REx, which is literally just a container full of rocks from space. If that thing had obliterated itself in the same way, I don't think they would have been able to recover the samples in the same way without, a lot more issues.
We would have had a lot of caveats of possible contamination, but
right? We wouldn't get to know all that cool stuff about all the DNA and be able to,
Yeah, right. You may not be able to be sure it's true. The asteroid rocks are going to look different than the Utah desert that you land in.
That's true.
But let's just be glad they figured that out. Stardust used the same system as Genesis, but had the accelerometers right side up, which I believe it was the accelerometers that were installed upside down. And so they knew up was up and down was down and landed beautifully. So it's been good since then, and it's amazing and impressive that Genesis has recovered what they've recovered.
I also learned quite a bit about the fact that the Apollo missions were kind of the beginning foundation of this kind of solar wind study. And she talked a little bit about it in the conversation, but I wanted to talk a little bit more about all the ways that Apollo allowed us to not just study the moon, but also study our star.
Ooh, study our star. Yes, they had all sorts of experiments tied to it. First, a little note of significance of the moon in the land of solar wind studies is the moon is actually outside the Earth's protective magnetic field bubble for much of its orbit. It passes through the magnetotail, the part that gets pushed back of the magnetosphere. But whereas the Earth has these So when hitting it or passing by it due to the magnetic field, but hitting it, making pretty auroras, it's harder to actually collect things. So indeed, they had in their surface experiments a solar wind composition experiment, similar in some ways to Genesis, foil sheet collected little particles. They just had a bunch of stuff. They had magnetometers, they had observations from the spacecraft, the command module orbiting around. And then they did observations of the sun. And by the time you got to Skylab, they did eclipse observations and corona observations. That was a follow-on from Apollo and what they were able to do process. So that's kind of a very quick smattering to say, yeah, Apollo, in amongst all the other stuff it was doing, the space physicists, solar heliophysicists got in there and started learning about the sun.
It's cool because we think of the moon as a great location if we want to do, in situ resource utilization, or maybe study how we can build permanent settlements on places like Mars. But not a lot of people think about it in the scope of solar studies. And it could be really powerful to have, more of a permanent presence around the moon to allow us to do that kind of study outside of the magnetosphere. But, we also got Parker Solar Probe and all these other things.
Also something you need to pay attention with human missions is that you've got more particles, both that and cosmic radiation that are getting through that, because the moon doesn't have a global magnetic field and isn't protected by the Earth's magnetic field for much of its orbit.
I imagine people living on the moon someday are going to have to tune in for the morning news. Like, there's an X-class solar flare on the sun. Make sure you bunker down from this time to this time. Like, that's going to be necessary someday.
I want to see you doing the lunar weather prediction. Yeah, I think you'd be great.
Oh, man, I volunteer as tribute. That'd be so much fun.
Bunker down. It's going to be a wild one out there today.
Well, on that note, do we have a wild random space fact to go along with it?
Oh, have I got a wild random space fact for you? I've got a wild random space fact. So the Soviets and later Russians carried guns on almost all of their missions. Early on, they carried them to the ISS. And what's wild with the original gun is it was a special design, the TP-82. It had 3 barrels, 2 shotgun barrels, small shotgun barrels. And they had ammunition for the shotgun barrels that were flares and that were also birdshot. And then they had a pistol/rifle barrel that would fire bullets, small caliber bullets. But then it was the part I haven't mentioned, it's in the survival kit. So the at least the public facing answer, which is all we'll stick with, is that they were, because they land on land and because they sometimes land where they don't expect to, the cosmonauts want to have some hope of fending off the Russian bear, Kazakh bear, bears and wolves. That was the theory. And so that's why they carried them in the survival kit, especially if they got stranded and had to hang out for a while before they were found. But then they had this weird gun permutation. It had a stock you could connect to this very large pistol, and the stock also functioned as a shovel and had a machete that folded out of it. So my understanding is somewhere early in the 2000s or late 90s, they switched to a standard pistol design. And then I don't think they carry them anymore in the Soyuz, but they certainly, for the first years of ISS, every Soyuz had a gun and ammunition. And I was researching this, and I'm still confused. And everyone's really, of course, they were always shady about it. And even NASA, whose people have trained, were shady about it. But I think they've theoretically stopped taking guns. But anyway, that's why, and that they did it. And there was a weird gun. And so it's a whole lot of, well, that's kind of weird.
That is super weird. I mean, I've heard about the astronaut knives and all the interesting kind of, self-protection and utility things that they bring with them. But you would think bringing a a gun into space, into something that is pressurized and could absolutely kill you if you blew a hole through the side. That is wild. I'm going to have to learn more about that. That's a good one, Bruce. 10 out of 10 random space facts. I've never heard anything about that. That is awesome. Weird bit of history.
Yes, I scored as Sarah hadn't heard about it. All right, everybody, go out there, look up the night sky, and think about bark on trees. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week to bring you some of the latest in space exploration. We've got several exciting launches coming up in the next few days, so we'll be watching closely to see how that unfolds so we can share it with all of you. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members whose support has enabled other sample return missions and deepened our understanding of the building blocks of our solar system. You can join us and be a part of the next wave of space discoveries at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.